So this is interesting. I just saw this. There is a new Android attack that sounds pretty awesome. I'd like to add this to the Android class if I can figure out how to do it. Checkmarks has found that if you install a malicious app that doesn't ask for anything except access to the storage, they're able to use that to bypass the security model entirely and gain control of the camera and the network. So they can take pictures and upload them to a remote site without your consent. So that sounds pretty awesome. I know this has happened over and over and over again. Android has this security model where it says this app needs access to the camera and the sound card and this and that. And there have been many, many ways to get past that, where you can do things even though you did not give it permission to do that. And this is another one in that category. So they took them a while to get Google and Samsung to care, but apparently both those phones are vulnerable. And if you have the old version of the camera app, it has this vulnerability. So I'd like to know more about exactly how it works than this article gives me. And especially the last time I taught the Android class, we got used Drozer and we got into the Android internals so we can see the signals that their apps are sending to each other. And this is the kind of attack that Drozer is made for. Drozer lets you see inside the app, inside the phone. And it was kind of disappointing because it was complicated to set up and then I couldn't find any apps with those vulnerabilities. All the apps I could find seem to have simple vulnerabilities like plain text network transmission. But this would be one of them where the signal sent from one app to another makes it possible to do something you shouldn't be able to do. So I'd like to get more information about this. I hope there are more write-ups and blogs about it to follow. A student told me about this, or I think Irvin told me about this morning. Portswicker has a free web training academy. I should check this out. Should definitely be added to my web application hacking class. By the way, that is probably the most important thing to put in the news. And remind me to talk later. The classes are going to be very different next semester. Probably everything on my website is not true. So let me put up a web page about this to remind me. I'll wait to the official time of the lecture. We need to talk about classes. It's going to be different. But anyway, next time I teach the web app security class, I should check this out. There might be some good stuff here to use for projects. People say it's a fun class. So Disney, just this week, opened Disney Plus, and they already got hacked apparently, or at least thousands of their accounts are for sale. Nobody knows what's happening. One person said it's just because people are using short passwords. Other people say it's because people are reusing password. Other people say, no, neither of those, they really got hacked. Nobody knows what's happening. But anyway, somebody is selling a whole bunch of Disney accounts on the dark web, and they've tested them, at least some of them are real. So something seems to be wrong with Disney Plus, and it's not clear yet what caused it or how big it is. Well, you mean people would know and they'll cancel those accounts or something? You would think so, yes. You would hope that the Disney people get a copy of this and turn it off. But if they're selling them for money, they might not be willing to buy it. That's right. But yes, hopefully if they know which accounts are compromised, they can do something about it. Or just force a general password reset or something, is things people often do. But so far, I haven't heard any response yet. Oh, no, I don't think so. Not if they go through Tor or something. Yeah, I mean, they go through Tor or something and do something quick with it. Like, I don't quite know what you can do with the Disney Plus account, but maybe you can order a bunch of products and have them shipped somewhere or something. You know,
so the Disney reuse their passwords.
Yeah, that's one I mean, I don't know what you do with it, but I assume there's some way to monetize a Disney Plus account.
$3, yeah.
Yeah. And so this one was kind of amazing. These teenagers are like 18 and they decided to catch pedophiles. So they went on online forums and claimed to be 13 and 17 until they got some teacher to come to meet them to have sex with them. And then they videotaped that guy and put the video up on YouTube. And when it was all over, then they said, hey, it never occurred to me, this might be dangerous what we're doing. And I was like, holy cow, that guy could pull out a gun. He could freak out. I mean, you could get the wrong guy. I mean, there's a lot of things that could go wrong here. That's why, you know, the cops said, well, you know, they caught somebody, but we really don't recommend that random idiots do this kind of work. It'd be a whole lot better to have like trained professionals doing it. It reminds me of when Anonymous, this is one of the things Barrett Brown did in like 2012. He said he was going to get a bunch of teenage hackers together and they were going to hack the Zeta drug cartel. And I said, don't do that. Are you out of your mind? Those are bad guys. don't mess with them. Leave that to like the army. He said, you're just a fascist inhibiting my freedom. I said, oh, I really don't. That you'd be lucky if that's all they do.
Yeah.
They're like they come to your house and just cut you in pieces. I mean, anyway.
No, how about that? A prosecutor who uses 13-year-old daughter to entrap somebody. It just happened just a few days ago.
He sent his 13-year-old daughter.
Yeah, she wired her.
Oh, I think I heard about that. Yeah.
No, he's in trouble.
Well, I would think so. Yeah, I mean, I don't think an underage person can reasonably consent to be bait. I think you know that's something like statutory rape. That's tricking them into something that they shouldn't have agreed to and probably shouldn't be considered responsible enough to agree to. Yeah, I mean, well, that's a terrible idea. Anyway, so I read this article, and their point is that maybe Google's going to kill Bitcoin. But the amazing thing I hadn't really caught on is Google's going to open checking accounts very soon, and so is Facebook, even without Libra. I don't understand how this is legal, but apparently Google has already been cleared to become a bank. This reminds me of an article that came out last week where they say Google already has access to a whole ton of medical data, which they had all along, and people just found out, and they said, never mind, you can trust the data you didn't know we had. But they had a partnership with some company, they got all this data. So Google's gonna be your doctor and your bank. And I heard some venture capitalists in a podcast saying all the big companies need to grow, but they can't grow in their lane anymore. So they pretty much have to expand into banking and healthcare. Those are the only industries large enough to add any capitalization to a company like Facebook or Google. So they're all going, and Amazon too, they're all moving into healthcare and banking. So they're just going to be everything. And it makes me want to vote for Elizabeth Warren. I mean, there's got to be some antitrust laws. How big are you going to let these behemoths grow before they rule the whole world? I mean, I thought there was already some rule that you couldn't just declare yourself a bank. I thought there was quite a chore to get approved to be a bank, but Google's going to offer checking accounts. So we'll see what comes of that. I know Apple has a credit card, but that's technically still from a bank. It's just like Apple branded or something. Maybe that's what the Google thing is.
So is the checking account a bank account?
Yeah. And I thought you had to be a bank to do that, and you had to have approval, and there was some limit. All the ones I know are tied to the big banks like Chase Manhattan or something. Well, China, I don't know how they do it. Chime?
CHIME.
I don't know that one. Yeah. Well,
I don't think it's a very small bank. I don't think they tie to any big ones.
Yeah, maybe not. I mean, there used to be some banking regulations, but they seem weaker. Anyway, let me see if there's any others. We're coming to the end of this. And this one was pretty interesting. They got a remote side channel attack that can steal money from the wallets for Zcash and Monero by doing timing. These things used supposedly timing-proof cryptography, but in practice, it doesn't work. And they're able to steal the key, so they can steal your private key and then they get your money. So that's pretty awesome. Anyway, we're up very close to the official time, I think far enough. Let me bring the important thing. I just got an email from our department chair. You probably saw about a week ago in the Chronicle, there was an article about City College saying their budget crisis is far, far worse than anybody ever thought. They need to cut $14 million from the budget by next semester, or their reserve will fall so low that they'll be placed under state control. So to avoid that, they're cutting everything. And what I heard from personal communication and now by email from the department, the email from the department chair said they published next semester's schedule, but they blocked all registrations so no students can sign up for those classes. Because apparently they are going to fire all the part-timers to save money next semester. And and that probably means I'm going to have to teach different classes. Probably none of this is going to happen. I'm probably going to have to teach like 106 and 120 or something because all the part-timers will be gone. And I would think we won't be able to teach advanced security classes next semester. They'll probably need the full-timers to all teach beginning classes to provide at least some of the core of the curriculum. Nobody's told me anything, but I'm just using logic. I mean, if they fire all the part-timers, that's going to blow big holes in the curriculum. So realistically, I don't know if any of this is going to happen. So I'll let you know as things proceed.
Were you going to pursue a private channel?
Yes. I have started a corporation. We have a lot of contracts. We just have a big contract with the military. I'm trying to save our part-timers and move them into that. And so they can work outside the college system. But it won't be classes here, it'll be classes elsewhere. And we're already teaching them in Sri Lanka and all over the place, and Singapore and China and stuff. So we're branching out to people that would like to pay for training classes. But apparently San Francisco doesn't want it, at least under the current administration. Now, I think they could easily fund this place by taking corporate money, but the current campus administration does not want to do that. So
Facebook or Google could say this.
oh, I think the person that would save us most is Salesforce. Mark Benioff gave an interview. I heard it. He said education is his #1 priority. He really cares about it. He would love to support us. I bet all we have to do is partner with him, put his name on a stadium or something, I imagine, or something like that. But the current administration of the college does not want to partner with corporations. I very much do want to, so I went to the private sector where you can do it. I have no problem prostituting myself to corporations. As far as I'm concerned, we're vocational education. The whole point of our classes is to get people jobs at those corporations. We should be obeying their wishes. But there's an older model where we are like priests with the holy, pure knowledge, and corporations are like evil and dirty and beneath us. Yeah, that's right. I totally don't feel that way. I totally feel like that we should just do whatever corporations need. Our job, we're here to hold up the military-industrial complex and help our students get jobs and be wage slaves. I'm all for that anyway. Yeah.
Would you be leaving your old project, your old class?
Oh yeah, I'm not going to take old stuff down. It'll be up there. But I kind of doubt I'll be allowed to teach these classes next semester. If they really do fire all the part-timers, then I think we'll have to like divvy up the classes among the full-timers. And this will change greatly. Anyway, so it's all up in the air right now. Anyway, this class still gets to go on for a while. So we'll talk about covert malware launching. So if you launch malware, back in the days of MS Blast, which was around 2007 or so, there was the blaster worm, and it would just run this process called MS Blast, and all you had to do was go in Task Manager and kill the process, and that would stop the malware. So that was the old days. And in order to prevent that, they try to hide their malware more carefully than that. So they use covert launchers. Now, the point of a launcher is you launch a program. The program has malware, but the malware is not in the executable part of the program, so your virus scanner and stuff won't catch it. This still works. You can make this stuff in Python and such. You put the code in something like the resource section, where it's just supposed to be icons and such. You put the code there, and then the malware loads that code into a DLL and puts it in memory as it runs, so it launches it in a different way than the normal way something is launched, so it often won't get caught. It can be encrypted or compressed, and so it will extract it using API calls that refer to the resource to remove the data from the resource section, and then it will stick it in memory so it can run. And there are various ways to do that. Process injection is the most common way. DLL injection and direct injection. By far, DLL injection is the most popular because it's very easy. I mentioned before in several of these classes, Windows is extremely unsanitary because it adds extra code at runtime from another file or from just code it finds in RAM. The point of Windows is to make programs small and to make them load fast and to conserve memory. So if it needs to have like an API call, it doesn't load its own copy of it. It finds one in RAM that's loaded by a previous process and just uses it, or it reloads a DLL from somewhere. And this makes Windows under normal circumstances faster and better, but it's also dangerous. So I just trick it into somehow loading another DLL and inject code into a running process. And this means it'll often bypass your security process because that process has already passed whatever tests for launching and getting network access and so on. And adding more code to it after it's already running will not generally trigger a retest. So that's the game here. So you will do virtual alloc to allocate space in another process's memory and then write to memory, and you can change what a running process is doing, and it will just continue to run with the privileges with which it was launched. This is pretty nasty. So that's what you mostly do is DLL injection. You run load library, and that will load another DLL into the process. And that as soon as it's loaded, that DLL will call DLL main. So all you have to do is put your malware in DLL main, and then just calling load library is all you have to do to add a malicious activity to a running process. So if you want internet access to download more code, but of course the Windows firewall will only let certain applications access the internet. So if you launch a random application, it won't let it access the internet. So you just inject it into the Internet Explorer process. And now your injected code will inherit the privileges of that process there. This all sounds very much like what they're saying they were able to do on Android. They were able to have another app which just by writing to the file system was able to move over and steal the data from the camera app. Same kind of thing. Anyway, so you gain the privileges of the code you're injected into. So if I have iExplorer over here, in memory, I can just inject a DIL into it, and now the Internet Explorer is running Trojan code, which was not, I did not actually infect the disk image, iExplorer, but I infected the copy in RAM, and now I get the ability to reach the Internet. So here's the pseudocode for that. You have a victim process. You call it to open the process to get a handle. Then you write to it. You write in some code, and then you load a library to add a DIL to it. So that's the game here. You can load any DIL you want into any process. Now, so here's a debugger view of it. You get a handle to the process, then you call virtual alloc x at 2 to get some memory. Then you write to the memory, then you get a module handle, and then you load the library into the memory. So after you've modified the DIL, you add it in, and now it injects the modified DIL into that process, and you have gained code execution with the privileges you didn't have. So, all right, if you find this in disassembly, you can look for strings. It will contain the name of the malicious DIL, the name of the process. You can also put a breakpoint in and interrupt the process to see what it looks like in RAM, or ways to see what it's doing. And then, of course, the more difficult but sneakier technique is direct injection, where you do not load another DIL. You actually change the code of a DIL that's already there. So you actually have to modify code that's already running, and often you will break the process by doing this. So this is more difficult and custom, but sneakier, of course. And then there's process replacement, which we've seen in the projects a while ago, where you run a program and you just pause the program, replace all the contents, and then resume it. So it's running a totally different program in RAM than was appearing on the disk. This is a pretty good technique. The trick is you must be able to suspend the process. Some processes are able to be suspended, others are not. So you suspend it, then you modify it, then you start it up again. All right. And so you'll see you create something suspended, and then you create a process down here from the suspended process. And then you unmap the view of the process, you allocate some new memory, you write into that memory, and then you set the thread context so when the process resumes, it's running with a different block of memory. So you change what's inside there and let it run under the same name. This is something I recommended years ago when there was a teacher that wanted to teach an Internet of Things class and we couldn't get it approved through the curriculum committee. I said, we'll just teach 106 and actually change all the contents without changing the name of the catalog. They didn't go with that, but I thought it was awesome. And I got it from this idea of process replacement. As long as you tell the students, we can still teach the class. Of course, then all their transcripts would be wrong and stuff. So it's sort of horrible, but you know, that way the guy could at least teach the class. But we found another way to do it. Anyway, that's the game here. You unmap the view of the section, allocate new memory, and then write process memory to put malware in it. And then you set thread context to restore the process's environment and resume the thread to start it again. But now the RAM is different. So you may remember there was a thing called the cold boot attack to steal the password from an encrypted drive, which is similar. You freeze the RAM, take it out, and put it in another machine and read it over here. That's essentially what you're doing here.
It's going to be 6 inches away.
Yeah, that's right. Well, actually, you have 10 minutes. If you cool it enough, it'll hold the memory for 10 minutes without power. So
it's time dependent.
yeah, but you'd have most of it in there, so you probably could still get the key or most of the key, and brute force the rest, I guess. Yep, Applebaum was one of the guys on that. Haven't heard from him in a while.
Yeah, what is he invisible now?
He seems to be in hiding somewhere, as far as I can tell. He probably got drummed out of everything. And
yeah, sex charges again.
Yeah, the same old thing, you know, molesting people or abusing people, like the senator, the Democratic senator had to quit.
Which one?
The comedian.
Oh,
yeah, I forget his name. A bunch of people.
Franken.
Al Franken. I mean, people just sort of vanished from public life. I guess they're still hiding. It's kind of a shame, but anyway. So I got some cahoots about it. Yeah, I don't like it much because the Democrats all give up and leave. The Republicans just stay in office and continue to run the place. So maybe it wasn't so brilliant for all the Democrats to leave over these things. It seemed like the right thing to do, but since it doesn't really matter, nobody cares. Republicans can just stay in office with like 16 or 20 people claiming they've been molested like Trump, then, you know, maybe it's self-defeating. That's what I said about Franklin. I said all he has to do is change parties and he'd be fine. All right. All right. 10 people online, so there could be a few more joining, I suppose. Oh yeah, some people still coming in. All right, looks like 7's it. Anybody in the room still coming in? All right, no screams of protest. Let's do it. Okay, where do launchers get their code? Okay, from the resource section, where they stick images and such. Which technique requires customized code? As direct injection, you have to carefully write code that fits in, mingling with the existing code. I've been writing 16-bit assembler all week, which I'll show you later, and it's really hard. Very difficult to make it run. Anyway. So which technique uses a suspended state? That's process replacement. You suspend it, change the RAM, and then resume it. Changing the RAM while it's running would be kind of nuts, and they won't let you do that. Yeah. Which process uses find resource? That's extracting the resource from the resource section so you can then write it into RAM. And what's the most common way to launch stuff covertly? DLL injection, the #1 way to launch malware on Windows. All right. So it looks like Mhino and Rich and Ken, okay? Yeah, they've increased the drama. Anyway, all right. So there you go. Anyway, all right. So then there's hook injection. And this is now, like so many things in Windows seem like they're designed for malware, but this is because Windows is the general all-purpose operating system. So you can hook signals. Windows processes send signals to the same process and other processes, just like Android sends intents, just like there are interrupts for the system as a whole. There's a way for one process to send a message to another, and you can hook that. So the point is to put a malicious hook that will do something bad. So you might have the user doing things like hitting the keyboard, and that would be an event that would go to the OS. It would send a message to a thread, which would be something like Microsoft Word picking up that you pressed a key press, so it's time to draw another letter on the screen. But you could put a malicious DIL in if you could hook, and then it would do extra stuff with that message before it reaches the application. And so local hooks are things that catch signals from one process to another part of the same process, and remote hooks go from one process to a different process on the same machine. So they're not remote physically, they're just remote logically. And so you got high-level remote hooks that require that the hook procedure is in a DIL, and low-level remote hooks that require that the hook procedure is in the same process that installed the hook. And all right. And so typically you're thinking of keyloggers when you think of hooks. That's the obvious thing. You want to catch key presses, which are messages sent to applications. So you can use procedure WH keyboard or keyboard LL. And so you call SetWindows hook. It's just a normal API call. Setting a hook is a normal Windows function for things like a Bluetooth keyboard or something. And so you have parameters, type of hook and the handle to the DIL and the thread ID to associate it with, and so on. Microsoft just has the ability to add a hook. It's not necessarily malicious, but you can use it for malicious purposes. So if you try to load your hook into all threads, then it will probably slow down the machine. That's going to bog them all down. Keyloggers log into all threads to get all the keystrokes. Other malware would target a single thread. Now, if you want to do one simple malicious thing, like steal the keyboard hash, steal the password hashes, then you don't want to hook into all processes. You want to hook into just one process, and you want to send a signal to activate your hook. So you can hook, there are signals that are almost never used, like this one, WHCBT is a computer-based training message. So you're probably not using it. And so that's a good one to use. So here's what you do. You'd load a DIL called hook.dil. Then you'd make a procedure address and call next hook, and then you send a message. So this is how you hook into Notepad. You then force it to be loaded by Notepad, and it'll then run in the Notepad process space. And that's what you see here. So you have a pointer to hook.dil, and you call load library. Then you have a pointer to your malware process, and you get the Notepad thread ID, and then you set a Windows hook to hook that process into Notepad. It's all Windows API calls running as intended. So then there's another Windows thing called detours, and I think the point of this was to make old applications run on newer operating systems. But you can modify applications in the OS by adding another section to the PE file. You already have the text section and the resource section and so on. Now you're going to have the detours section, which modifies the structure, and this will have different import addresses so that you call different functions. So you'll see it here. You've got text, data, resource, and then detour. And in here you've got another import name table with different functions. So this is a way to change the behavior of an executable. So that's another way to modify it. And then there's APCs. APCs are asynchronous procedure calls. If you write networking handlers in a language like C, you have to get used to these things. If you are trying to do something like a handshake, SYN, ACK, ACK, you have to wait for the handshake, and you don't want to freeze the computer while that happens. So you have to have an asynchronous call, something that will happen at a different time, not just linearly proceeding from step 1 to step 2. And you can add, every thread has a queue of asynchronous procedure calls, because remember, threads can move forward independently. So anyway, when your thread is in an alterable state, then these APCs are called. So there's things like wait and sleep that you do to stop one thread, and you can add APCs to it, and they'll run later. So there are kernel mode APCs and user mode APCs. You can inject in both cases. You can just add another item to the queue, and it will then be processed at some later time when that thread gets a chance to move. So you can use a queue user APC. You can do an APC injection from user space. And this is wait for single object EX is the most common call. Many threads are waiting their turn to run. That's the whole point of Windows. Windows doesn't want the processor to be waiting for slow things like the keyboard and the RAM, so everything is moving forward in threads so that one thread can move forward while the other threads are waiting for their turn or waiting for some slow thing to happen. So you can call this queue with a handle to the thread and a parameter to the function, and you can just add something to the list. So here it is, opening a thread at 1 and loading a library at 2. And there's a DIL name here. And then you can add it with these just simple function calls. And you can do it from kernel space. This is used, if you're in kernel space and you want to run a user space function, it's hard. The two are pretty separated, and APCs is one way to do it. You can now use these kernel calls to add a userland APC to make something happen in user space if you're a rootkit running in kernel space. So there you see it going, kernel initialize APC and kernel insert queue APC. I see a chat message coming in. Is there an event manager or something that talks to the APC? Not as far as I know, but I'm far from an expert. I think it's very simple, like interruptions, just things waiting in a queue, but I don't know. There may be some event manager. It's a good question, and I don't really know the answer. Anyway, so I got some cahoots about this, and then I want to talk to you about the MBR malware, because I added a lot more to that project, and I think it's a lot of fun. So first, let's do the cahoots, which are 12B. And here. All right. All right. I'll give it a few more seconds, but I think 7 is all we had last time. Aha. All right. I'll give it a few more seconds. All right. I guess we got everybody that's coming. Okay. So, which one of these will hook all processes? All right, keyloggers do that. These other things may or may not, but detours certainly won't. But keyloggers do hook all processes typically. Which technique manipulates a message from a process to itself? Okay, that's a local hook. That's what's meant by local. What's meant by local. All right. So which technique puts a new section in the PE file? That's detours, good. APCs do not go in a new section. And which technique lets a kernel mode rootkit execute user space code? Okay, that's APCs, asynchronous procedure calls. And which technique only works when threads are in an alterable state? That's APCs. You can only add things to the queue when it's in what's called an alterable state. All right. So I've got Ken, good. And Anton, okay. I've got to spell it better. And Yamani, all right. If that's a real name, I'm not sure Yamani's a real name. They might want to tell me who they are if they want credit. But anyway, it might be a real name, but it's not one I've seen before in this class. Anyway, so let me talk about the next project, which I promised you last time, and I did get it working. Like I say, I spent all week writing 16-bit assembly code, and I managed to get a couple things working. So we're here in 126, and these projects are kind of out of order. The bootkit analysis with Box we did before, you used an encrypted malicious bootloader. And I decided doing that one, I really didn't understand the primary boot up sequence. So I made one just to understand how normal boot up works. And we do put a modified bootloader in here, but only a very simple one. So here, I went through this, and this was really good for me to go through, and I think it'd be good for you too. So when computers boot up, they start out the way computers were like 45 years ago, and they gradually move forward in time. So you start in the BIOS. The BIOS is in the ROM chip, and it checks to see what hardware is out there, and it finds if there is something to boot from, like a floppy drive or a hard drive. If there is, it then calls the master boot record, which is the first 512 bytes on the bootable device, which is typically a hard drive these days. And that's the master boot record, then calls the boot sector of the active partition. It finds a partition somewhere that is bootable, and it goes to the active partition, which then calls a bootloader, which might present the user with a list of available operating systems and choose one, and then it'll load the operating system like Windows or Linux or something. So the master boot record is always 512 bytes long, and it has bootstrap code, which is most of it here, and it will just run that code whatever you put there, which is why boot sector viruses are so awesome. This code runs in real mode. When the processor boots up, it starts out the way processors originally were, in a real mode system that only has 12 bits to address memory, so it can only have a maximum of 1 megabyte of memory. And it directly refers to that memory. This whole thing is called the master boot record. It's got bootstrap code. It's got a partition table, which in the old FAT system, or in the old MBR system, you can only have 4 partitions, and each one of them has a 16-byte record. And then it has a boot signature, which is always 55AA. It won't accept it unless that's there, just to indicate that this is indeed a master boot record. Then, so you run the bootstrap code, and the bootstrap code identifies the active partition and transfers control to the partition boot sector, which is on the partition somewhere else on the disk. This partition record will tell it where it's located on the disk. Then it goes here and it finds another sector like the first one with the same mark, 55AA, and it's got a jump command right at the start to jump into the bootstrap code, which will be somewhere here. And that then often has more and more and more code, because the code has to be bigger than 512 bytes often, and that will then run the bootloader, which will launch something like Linux or Windows. So you can do this in FreeDOS. And so I put DOS in the Box emulator. I found a download that came at Box from a long time ago, which is FreeDOS, which is pretty mind-blowing. So you've already got Box installed, and to make it boot FreeDOS, you just have to use fdosmini.img, which is a file you can download, and then you specify some generic stuff here, and you can launch it there. So let me launch FreeDOS. I've got this all running on my Windows machine here, and I see a chat message coming in. Oh, good. Abdel Yamani, good, fine. Yeah, glad to have you along. Okay, good. If you do any quizzes, we'll find a place to put your score. Anyway, everybody's welcome, of course. So now I'm going to run this thing, which is here. Now I'm in the FDOS directory. Let me do a dir and see what files I have here, because I've been making various modified bootloader files here. But the fdos.txt, I think that is the original one. Yeah, fdos.txt. So it is boxdebug.exe minus q minus f, I say, all right. And then fdos.txt. Okay, this should launch the Box FreeDOS. Now, by default, it launches in a debug mode, so it loads just like any other debugger and then pauses right away. And if I just hit continue here, it will just continue to run. And what it'll do is start printing messages here. It asks you some questions, press F1 or F12 or something, and if you don't, it will go to FreeDOS. That's it. Now it's actually loaded up DOS. This is, a blast from the past. This is DOS circa 1980. And it's a free version, so I don't have to deal with Microsoft copyright issues. But anyway, that's all I got here. A very simple DOS that boots up, and you can issue DOS commands here, but I don't really care about that. I want to look at the process that went on in the early stages of booting. So to stop this thing, you just click here and hit Control-C several times, and that will stop it. So now we can mess with the bootloader. So that's the emulator. You see it going. Now let's take a look at the structure of the MBR. It's got 446 bytes where you can put any code you want, then 64 bytes of partition table, and then 2 bytes for the signature, and that's all. And this code can be anything. All right, the partition table just has 6 16-bit records specifying the table entries, and each table entry has cylinder, head, and sector for where the partition stops and where it starts, referring to the actual physical layout of the old spinning hard drives. And it has other information there like the partition type and an indicator of whether it's active, which Linux doesn't seem to need, but Windows does need. You have to have an 80 here to make a partition active to make it bootable. So you can view this thing in HXD. So we just booted this thing from fdos.txt, and that loaded it from this file fdosmini.img. And I can look at that thing in just a hex editor like HXD. So I'm going to launch it as administrator, because a lot of this stuff is, I'm in the programs file directory, and you pretty much have to be administrator to use files in there. And here's fdosmini.image. So if I load it, here it is. This is the glorious boot sector in a raw hex editor. And if I make my window a little bigger, then you can see from 0 down to 200, and right here at the end is 55 AA. So that is the boot sector. Boot sectors are 512 bytes long. All sectors on floppies and hard drives are 512 bytes long. They've been that way for a very long time. And so it is 100 in hex is 256, and 200 is 512. So this, which I would highlight if my mouse would cooperate, there we are. So that is the master boot record. And the 55 AA is the mark, and before that is the partition table. So if you just drag straight up, you get 1, 2, 3, 4 16-bit sections. That is the partition table. And you can see this one starts with 80, which makes it the active partition. And then it has some numbers here like 0, 1F and so on, which are like the first start of it and the finish of it in that crazy cylinder head sector notation, which is a little hard to interpret, but it refers to which sectors begin and end that sector. And you can see the next 3 partitions are empty. They're all just zeros. So this disk has only 1 partition, which is where FreeDOS is loaded. And this is the executable code, which is why you see it all being pretty much gibberish, except for a couple strings, something here like default and something about amoeba or something, Unix Novell amoeba. Those are the strings for messages, and this is the executable code. So you're seeing it, and it starts, notice it starts with 33C0, just as a reference point. So now we saw the executable code starts with 33C0, and when you load the machine, that goes to address FC100. So if you start this thing again, it automatically breaks right away, and you can use this debugger, which is very nice. You can do LB 0x7C100. That will put a break at the start of the master boot record. It always loads to that address, 7C100. Now, if you continue from this point, it runs through the BIOS and prints some messages here where it's starting to boot, but then it stops again because it's reached this point. And I can now unassemble /10 commands, for example, and I will now see the 33C0, which is what I saw before. These are the commands. XOR AX to AX will put a 0 in AX, and on it goes doing stuff. What it's actually going to do is copy a bunch of data to address 600. So let's follow through this a bit and see what it does. Let me go to my instructions and make sure I haven't skipped anything important. Right, so we run it. Now we can trace on, and now we can step through it, which is very nice, and we can watch it go. So here's the MBR, where we are, and there's the C033 and the A5. You can examine it the way we did in the exploitation class, we do spend a lot of time in the GDB debugger, and we can do the same kind of thing here. We can do x/128x from 0x7c100, and that will give me the same information that I saw in HXD, except instead of looking at the hard drive, I'm now looking at the contents of RAM. And so here's 7c100. Let me move this out of the way as much as possible. And 7c100 starts with 33c0. You see it here. Remember, things are kind of backwards. And it goes down to 55AA down here. And so this is the master boot record. And if you want to examine the code, you do what I did before, just U/10 or something, and that will show you 10 machine language instructions. Now, let me make my window a little higher, make it easier to see in the classroom. All right, and let's go back to my instructions. So now we've seen this. Now, if you look at this, you'll see a rep-ne. The rep-ne command is what copies data. So what you see here with rep-ne, that's going to move a bunch of data from the location pointed with DI, from SI to DI. And you can see SI, I'm not quite sure what's in SI, something, 7c100 followed by something. It's going to, SI is pointing ultimately to the start of the master boot record, and DI is pointing to 0600. So it's going to copy the master boot record to low memory, starting at 0600, right in the first couple of pages of memory. So that's pretty awesome. So let's take a look at what's at 0600. We can do an X128 again and look at 0600. And if we do that, it's all full of zeros right now. I'm going to scroll back a bit. There you can see it's all zeros. There's a little bit of data down here in 730, but all the way from 600 up to 700, there's nothing but zeros. But if I run this code, that's going to change. So let's take a look at the code again. And I was real happy to learn about the trace command here that makes it real easy to watch what it's doing. So if I unassemble 10 commands, oops, got to use lowercase. Okay, I will see down here is where it's going to start copying. So I'm going to just from trace on and then step through these one by one. So it's going to do an XOR, and eventually it's going to do a rep-ne. So I can just step and step and step, and it's going to show me the commands. This is a move and another move and another move. This is with the 7c100, that's the from address. Then it's going to load the to address here, 600, and then it's going to do the number of bytes, which I guess is 100 to move, and then it's going to do the rep-ne. So if I do one more, it's going to jump. I think it's doing the rep-ne, and I don't know if I have to, it's going to do this over and over. Yeah, I guess it is. All right, so let me see how I got through this before. Yeah, I loaded a breakpoint after it. So let's go back and unassemble /10. The rep-ne is going to loop around and do it a lot of times, so doing it step by step is annoying. So I'm going to put a breakpoint here and continue. So it will finish all the reps of the rep-ne. So it's load break 0x7c16, and then continue. And it does all those rep-nes because I left trace on, it shows me all of them, and now it's done. And now if I look at the memory near 600, it should be full of stuff now. And there it is. And as you can see, this used to all be zeros, but it's not anymore. In fact, it's the same old stuff, C033 all the way down to the end of the, anyway, this is a one page of the master boot record, not the whole thing, but the first 100 bytes, which is 256, 100 in hex. Anyway, so it's copied stuff to that location. And now I can proceed through the jump F. So let's go back to here and see what's happening. If I do unassemble, and try and make it fit on the screen better. Maybe I can make this wider. Okay, if I unassemble /10, I'll see where I am. So now I've got to do a jump F, which is going to jump into the code I just wrote, into the middle of it, jumping to 6667, and then continue. So I can do a step, and now it moves to 6667, where it's got this, and now it's going to execute code down here for a while. And all right, so I can do 30 S's, and then I will eventually have an interrupt 10. So if I think I did an S30, and it now does an interrupt 10. Interrupt 10 is what prints out characters. So it printed something out on the screen, and I don't think we're seeing anything. There might be something boring like a carriage return or something, and there's a flag to get here, but you can see the characters one by one. So if I put a breakpoint at 070E, because if I look here, you can see the interrupt 10 is at 0712, and if I examine that area with unassemble /10 0x 070C, for example, then I can see what's going on here. It was doing this load SB thing, then a push. Here's the int 10, and then it does something else, and then it might do another int 10. So if I break at 714, that should do it. Is that what I did before? Before I did 070E before it, either one would work. I guess I'll do 070E to be consistent. So I put a breakpoint at 0x 070E. And now if I just do continue, it will go there, and I could turn trace off to make it faster. If I keep continuing, it'll eventually start printing characters I can see. There we are. It's starting to print out F1 stuff here. So it's calling the print routine, and it was printing stuff I couldn't see, and it eventually got around to printing stuff I could see. Although to be fair, the interrupt 10 is used for other things than printing. So there's another parameter in there. So anyway, the point is you can see what's going on with the code here. And so now we can make a modified bootloader, which is pretty awesome. So let's try this one. Here is a, let me make this one, aboot.asm. So I did it on Linux. You could in principle do it on any operating system, I suppose, but I'm accustomed to doing it on Linux. So I wrote this thing called aboot.asm. It took me a while to write it, and turned out to be possible to write this very simply, which is the way I like things. Almost nothing to it. Bit 16 tells it to compile it as 16-bit code, not 32-bit code, because at this load step in the boot up process, we're running in 16 bits. Now, I didn't bother to define any start or anything because I don't really want to make runnable code on this operating system. I just want to get the code and stick it in the bootloader. So all I want to do is put 0E41 in AX and call it 10. 41 is our old friend capital A. So this, the 41 is the character to print, and the 0E is the code saying print. So the high 8 bits in A tell it what instruction to execute, and the low 8 bits in A are the character to print. So this should print a capital A on the screen, and then I halt. That's it. So it is really very simple. And you can assemble it with NASM, and I should have a NASM in my up there area. I can do NASM, format binary, and I want to do a boot, and I want to put the output in, say, a boot.bin. That's, I don't need the capital though there. That's all this is going to do. Use the NASM assembler in format of binary to compile it and make raw binary. And it would complain if something was wrong. Now, if I want to see what's in the raw binary, I can just use good old XXD. XXD is the command line equivalent of HXD. It's very, very nice. A boot.bin. It shows me the raw hex, and you can see it there. BE41 0ECD. It's only 6 bytes long, that code. That's all you need to do it. And you can put that right from here, right into the boot sector. You go into your Windows machine, and so I'm going to get out of here, and I'm going to copy a clean hard disk. So I go here, and I do a dir. Now, the hard disk I was using was fdos mini.image. So I'm going to copy fdos mini.image to fdos a1.image. Okay, now I'm going to need a text file to boot from it, but I'll do that later. Now I'm just going to take this FDOS A1 and I'm going to modify the boot record. Let's check my chat message. Have to go. Okay, fair enough. Yep, well, I'll have the video up. All right, so I got FDOS A1. Now I run HXD and I modify FDOS A1, which is here. Okay, so this is the original bootloader, and all I want to do is put the 6 bytes on top of there. So I can just copy them right from here. If I highlight them, they automatically copy in the Google console. And if I go back to here, I can do edit, paste, write, and they turn red. That puts those 6 bytes on top of the stuff that was there. And now I just save it by clicking the disk, and that's it. Now, I do need to make a text file to specify this. When I booted this thing, it had to boot from fdos.txt. So I need to copy fdos.txt to fdos a1.txt, and then notepad it, fdos a1.txt. And you'll just see here, I had the name of the disk and I need to change that. That's all I have to do, A1. Now it'll boot from my modified bootloader. So I save this. And now I run it the same way I ran stuff before. So I'll just up arrow a couple times. There I am running something. And all I want to do is run FDOS A1. So that'll load it and then pause at the bootloader. I can unassemble. Well, first I could load a breakpoint at 0x7C100 because I have to proceed through all the BIOS code to get to the bootloader, to get to the master boot record. So I do that and then I continue. And by the way, it has to do a lot of instructions to run the BIOS. You can see from the time which appears here, the time is now 50 million ticks. It took 50 million clock cycles to get to the MBR. But that was all running in the BIOS. Now I'm up to 7C100 and I can examine it with U/10. And remember, this used to start with CCE0 and now it starts with other stuff. Move AX, int 10 and halt. This is the 6 byte modified code I put there. So if I look there, I can do a step and another step and another step. And it ought to print an A, but it looks like something didn't work. Continue. There. If I continue, it finally prints an A. I know why. When I stepped, it stepped into the int 10 BIOS code, which would probably be thousands of more instructions. I have to really continue to see it because it doesn't seem to have step over and step into like more advanced debuggers. So I just had to continue and you see it printed an A. That's all this does. But I still remember the thrill when I first printed an A from a C language. I was very proud of myself, very happy. This means you can do anything. So,
hello world.
What's that?
Hello world.
I printed an @ sign on the screen of my VIC-20 from machine language, and I was very happy. The same thing. Hello world was too advanced at that point. That was the first time I figured out where the video memory was and how to write to it and how to load the accumulator and output it. I said, I could do anything. I rule the world now. Anyway, so, all right, so that's the game. So there you go, and that's the second part. And then there's another one where you make cyber hacker. You can print a whole message on the screen. This is like hello world. It took me days to get this working, by the way. It may look simple, but I had a lot of problems, but this is the code that does it. So you have to put that code in Linux is the way I did it, then compile it with NASM, then put it in the bootloader like this. And when you run it, it will print Cyber Hacker, which is the name of a game that Caitlin was playing last weekend. There's a game you can load on your phone called Cyber Hacker, which she was playing, and I thought that was a great name. So anyway, all right, so check it out, and I'll probably add even more to this. I'm hoping to make one that reads from the keyboard, and then you have to like type in a special character, and you'll have to read the code to figure out what that character is, but I can't get it to read from the keyboard yet. All these things are far more difficult than you might imagine they are. But anyway, it's good, clean fun, and I'm hoping we'll eventually get up to more modern bootloader attacks after we learn these earlier ones. But that probably won't be till next semester. Anyway, so that's what I wanted to show you. If you got any questions, let me know. Other than that, I'm going to I guess I'll stop the recording and leave the share going for a little while. See if anybody wants anything.